In today's video, we're going to look at how we can solve linear systems by using matrices. The ultimate process boils down to writing the system as the augmented matrix and then row reducing that augmented matrix. Now, in the previous video, we saw that the elementary row operations were identical to the operations that were performed on linear systems. This leads to a method of solving linear systems. We set up the system as its augmented matrix. Then we either reduce it into REF or reduce it into RREF. Right, so our theorem, let AX equal B and CX equal D be two linear systems, each of M equations in N unknowns, if the augmented matrices A augmented with B and C augmented with D are row equivalent, then the linear systems are equivalent. And the proof is very simple. It follows from the definition of row equivalence and from the fact that the three elementary row operations on the augmented matrix are the three manipulations on linear systems which yield equivalent linear systems. Corollary: if A and C are row equivalent M by N matrices, then the homogeneous systems AX equals 0 and CX equals 0 are also equivalent. This follows directly from the theorem simply by setting B and D both to be the zero vectors. Now for the actual method itself. So the idea consists of starting with the linear system AX equals B, then obtaining a partitioned matrix C augmented with D in either row echelon form or row reduced echelon form, that is row equivalent to the matrix A augmented with B. Now, the matrix C augmented with D is going to represent the linear system CX equals D, right? Which is quite simple to solve because of its structure. And the set of solutions to this system will give precisely the set of solutions to AX equals B because the two systems are equivalent, meaning that they have the exact same solution. The method in which we put A augmented with B, so the method in which C augmented with D is in row echelon form is called Gaussian elimination. The method where C augmented with D is in row reduced echelon form is called Gauss-Jordan reduction. Gaussian elimination is the matrix equivalent of method of elimination. Once you get it into REF, you're going to have a precise solution for one of your unknowns, and then you must use backward substitution to find the remaining. Gauss-Jordan reduction requires no back substitution. It will give you an exact solution for every single unknown. For this purpose, for this reason, the method that will most commonly be used is Gauss-Jordan reduction. And in fact, that is the method that's going to be used in the example. Okay, so apparently I do not know my own examples. I had misspoken. Actually, we're going to solve the system using both methods. We'll start with Gaussian elimination and then proceed on to Gauss-Jordan. So first, for Gaussian elimination, what we want to do is set up our augmented matrix, right? So remember, the augmented matrix for the system is the coefficient matrix, which is 1, 2, 3, 2, negative 3, 2, 3, 1, negative 1, augmented with the constant vector 6, 14, negative 2. And the idea is to REF this matrix. Once again, I will be using a calculator to help me keep track of each step. Menu. When setting up the augmented matrix in your calculator, number of rows equals the number of equations. Number of columns equals the number of unknowns plus that additional 1 for the constant vector. To REF this, first thing, let's do negative 2 row 1 plus row 2, and then negative 3 row 1 plus row 3. And the result now at this stage, the process tells us to multiply the second row by negative 1/7. However, take a look. If we multiply this row, the second row, by negative 1/7, we're going to have a bunch of fractions, which are not fun. But if we multiply row 3 by negative 1/5, we get no such fractions. So what I'm going to do is flip row 2 with row 3. And then do negative 1/5 times row 2. Right? And now 7 times row 2 plus row 3. And this should just about put us in REF. All that's left is now to multiply row 3 by 1/10. Now we have to interpret this, right? So put this augmented matrix into its system. Right, this gives us x plus 2y plus 3z is equal to 6. Y plus 2z is equal to 4. And z is equal to 3. Right? Notice that last row tells us what z equals. We now have to do backward substitution to determine the remaining two. So plugging z equals 3 into the second equation, we get y plus 6 is equal to 4, and so y has to be negative 2. Then plugging both z and y into the first equation, x minus 4 plus 9 has to be 6, right? Negative 4 plus 9 is 5, so we have x plus 5 is 6. And so x has to be 1. So our solution written as an ordered triple is 1, negative 2, 3. Now for Gauss-Jordan. Again, you want to start by writing your system as its augmented matrix. And this time, instead of stopping at REF, we continue to put it into our REF. Now, no need to reinvent the wheel. We already have the REF. We did that for Gaussian elimination. All right, next step, let's do negative 2, row 3 plus row 2, and negative 3, row 3 plus row 1. All right, that'll give us this matrix. Now it's just negative 2, row 2 plus row 1. And we get this matrix. This is now an RREF. Now, at this point, again, you want to write this augmented matrix as its system. This would be the system. And notice that this immediately gives us our solution of 1, -2, and 3. Because of how immediate the solution becomes, and because it doesn't involve backward substitution, Gauss-Jordan reduction is the preferred method of solving linear systems. That concludes today's video on solving linear systems using matrices. So essentially looking at Gaussian elimination and Gauss-Jordan reduction. In the next video in this series, we are going to take what we just learned and apply that to now being able to find the inverse of a matrix in a much simpler way. That is, finding the inverse of a matrix by using row operations. As always, thank you so much for watching this video. I hope you enjoyed, and I will see you all in the next video.